Question 15, Part C. Two particles move along the x-axis. When t equals 0, particle P1 is at the origin and moving with velocity 3. For t greater than or equal to 0, particle P1 has acceleration given by a1 equals 6t plus e to the power of negative t. Part 1. Show that the velocity of particle P1 is given by v1 equals 3t squared plus 4 minus e to the power of negative t. The velocity equation v1 is found by integrating the acceleration equation a1. So v1 is equal to the integral of 6t plus e to the power of negative t with respect to t. So performing the integration, we get v1 is equal to 3t squared minus e to the power of negative t plus the constant of integration c, which we'll need to find. And we can apply a boundary condition for that. Now at t equals 0, v1 is equal to 3. Hence, 3 equals 3 times 0 squared minus e to the power of 0 plus c. Now e to the power of 0 is 1 and 3 times 0 is 0. So 3 is equal to 0 minus 1 plus c. Making c the subject, we get c is equal to 4. Therefore, the velocity equation v1 is equal to 3t squared plus 4 minus e to the power of negative t as required. When t equals 0, particle P2 is also at the origin. For t greater than or equal to 0, particle P2 has velocity given by v2 equals 6t plus 1 minus e to the power of negative t. Part 2. When do the two particles have the same velocity? To find the time when the velocities of both particles is the same, we equate v1 and v2. In other words, v1 equals v2. Now we found v1 in part 1 and we're given v2. So we can form the equation 3t squared plus 4 minus e to the power of negative t equals 6t plus 1 minus e to the power of negative t. Now we can cancel out e to the power of negative t from both sides of the equation, so I've crossed them off. So we're left with 3t squared plus 4 is equal to 6t plus 1. Now I'm going to move 6t plus 1 over to the left-hand side to form a quadratic equation. So we have 3t squared minus 6t plus 3 is equal to 0. Dividing all terms by 3, we get the monic quadratic equation t squared minus 2t plus 1 equals 0. Now if you notice on the left-hand side, we have a perfect square, which can be factorized as t minus 1 in brackets to the power of 2 equals 0. So t is equal to 1. Therefore, particles P1 and P2 have the same velocity at time t equals 1. Part 3. Show that the two particles do not meet for t greater than 0. In order to show that the two particles do not meet for t greater than 0, we need to show that the difference between their displacements is always greater than 0 for t greater than 0. So let's find the displacement equations for particles P1 and P2 and then consider the difference between those displacements. So let d1 be the displacement of particle P1. So to get the displacement equation, we integrate the velocity equation with respect to t. So that's the integral of 3t squared plus 4 minus e to the power of negative t dt, which gives us t cubed plus 4t plus e to the power of negative t plus the constant of integration capital D. Now d1 is equal to 0 when t is equal to 0. Now that's the boundary condition that's given in the question. Hence, 0 equals 0 cubed plus 4 times 0 plus e to the power of 0, which is equal to 1, plus capital D. And solving this equation for capital D, we get capital D is equal to negative 1. Hence, the displacement equation for particle 1, so d1 is equal to t cubed plus 4t plus e to the power of negative t minus 1. Let's repeat the process now for the displacement equation for particle 2. So let d2 be the displacement of particle 2. So d2 is equal to the integral of v2 dt, so integrating the velocity equation for particle 2. So that's the integral of 6t plus 1 minus e to the power of negative t dt, which gives us 3t squared plus t plus e to the power of negative t plus the constant of integration, capital E. Now I've used different letters for the constant of integration because they can be two different values. Now, using the boundary condition that's given in the question, d2 is equal to 0 when t is equal to 0. In other words, the particle starts at the origin when t is equal to 0. Hence, 0 is equal to 3 times 0 squared plus 0 plus e to the power of 0 plus capital E. Solving this equation for capital E, we get capital E is equal to negative 1. Hence, d2 is equal to 3t squared plus t plus e to the power of negative t minus 1. Now, our final step is to show that d1 minus d2 is greater than 0 for t greater than 0. So in other words, t cubed plus 4t plus e to the power of negative t minus 1 minus 3t squared plus t plus e to the power of negative t minus 1 in brackets. Now if we expand the brackets, collect like terms, cancel any terms where needed. So the e to the power of negative t here will cancel with this e to the power of negative t here. This negative 1 will cancel with this negative 1 there. And we end up with t cubed minus 3t squared plus 3t, which factorizes to t times t squared minus 3t plus 3 in brackets. Now we know that t is greater than 0. So this term here is positive. We just need to show that t squared minus 3t plus 3 is also positive for t greater than 0. And we can do that by considering the discriminant of the quadratic t squared minus 3t plus 3. And we calculate the discriminant using b squared minus 4ac and we get negative 3. Now because the discriminant is negative and t squared minus 3t plus 3 when graphed is a concave up parabola with no real roots. In other words, it won't cross the x-axis. So it's going to be positive for all real t. And I've stated that here. And we're also given that t is greater than 0. Hence, t times t squared minus 3t plus 3 in brackets is greater than 0 for t greater than 0. Therefore, the particles do not meet.